In mathematics, the Pythagorean theorem, also known as Pythagoras' theorem, is a fundamental relation in Euclidean geometry among the three sides of a right triangle. It states that the square of the hypotenuse, the side opposite the right angle, is equal to the sum of the squares of the other two sides. The theorem can be written as an equation relating the lengths of the sides A, B and C, often called the Pythagorean equation. A 2 plus b 2 equals c 2. Display style a caret 2 plus b caret 2 equals c caret 2, where c represents the length of the hypotenuse and a and b the lengths of the triangle's other two sides. Although it is often argued that knowledge of the theorem predates him, the theorem is named after the ancient Greek mathematician Pythagoras c. 570–495 BC, as it is he who, by tradition, is credited with its first proof, although no evidence of it exists. There is some evidence that Babylonian mathematicians understood the formula, although little of it indicates an application within a mathematical framework. Mesopotamian, Indian and Chinese mathematicians all discovered the theorem independently and, in some cases, provided proofs for special cases. The theorem has been given numerous proofs, possibly the most for any mathematical theorem. They are very diverse, including both geometric proofs and algebraic proofs, with some dating back thousands of years. The theorem can be generalized in various ways, including higher dimensional spaces, to spaces that are not Euclidean, to objects that are not right triangles, and indeed, to objects that are not triangles at all, but n-dimensional solids. The Pythagorean theorem has attracted interest outside mathematics as a symbol of mathematical abstruseness, mystique, or intellectual power. Popular references in literature, plays, musicals, songs, stamps, and cartoons abound. Pythagorean proof. The Pythagorean theorem was known long before Pythagoras, but he may well have been the first to prove it. In any event, the proof attributed to him is very simple, and is called a proof by rearrangement. The two large squares shown in the figure each contain four identical triangles, and the only difference between the two large squares is that the triangles are arranged differently. Therefore, the white space within each of the two large squares must have equal area. Equating the area of the white space yields the Pythagorean theorem. QED that Pythagoras originated this very simple proof is sometimes inferred from the writings of the later Greek philosopher and mathematician Proclus. Several other proofs of this theorem are described below, but this is known as the Pythagorean one. Other forms of the theorem. If C denotes the length of the hypotenuse and A and B denote the lengths of the other two sides, the Pythagorean theorem can be expressed as the Pythagorean equation A 2 plus B 2 equals C 2. Display style A caret 2 plus B caret 2 equals C caret 2. If the length of both A and B are known, then C can be calculated as C equals A 2 plus B 2. Display style C equals sqrt A caret 2 plus B caret 2. If the length of the hypotenuse C and of one side A or B are known, then the length of the other side can be calculated as A equals C 2 minus B 2. Display style A equals sqrt C caret 2 B caret 2, or B equals C 2 minus a 2. Display style b equals sqrt c caret 2 a caret 2. The Pythagorean equation relates the sides of a right triangle in a simple way, so that if the lengths of any two sides are known, the length of the third side can be found. Another corollary of the theorem is that in any right triangle, the hypotenuse is greater than any one of the other sides, but less than their sum. A generalization of this theorem is the law of cosines, which allows the computation of the length of any side of any triangle, given the lengths of the other two sides and the angle between them. If the angle between the other sides is a right angle, the law of cosines reduces to the Pythagorean equation. Other proofs of the theorem. This theorem may have more known proofs than any other, the law of quadratic reciprocity being another contender for that distinction. The book The Pythagorean Proposition contains 370 proofs. Topic: Proof using similar triangles. This proof is based on the proportionality of the sides of two similar triangles, that is, upon the fact that the ratio of any two corresponding sides of similar triangles is the same regardless of the size of the triangles. Let ABC represent a right triangle, with the right angle located at C, as shown on the figure. Draw the altitude from point C, and call H its intersection with the side AB. Point H divides the length of the hypotenuse C into parts D and E. The new triangle ACH is similar to triangle ABC, because they both have a right angle by definition of the altitude, and they share the angle at A, meaning that the third angle will be the same in both triangles as well, marked as θ in the figure. By a similar reasoning, the triangle CBH is also similar to ABC. The proof of similarity of the triangles requires the triangle postulate. The sum of the angles in a triangle is two right angles, and is equivalent to the parallel postulate. Similarity of the triangles leads to the equality of ratios of corresponding sides. B C A B equals B H B C and A C A B equals A H A C. Display style frac BC AB equals frac BH BC text and frac AC AB equals frac R AC. The first result equates the cosines of the angles θ, whereas the second result equates their sines. These ratios can be written as B C 2 equals A B times B H and A C 2 equals A B times A H. Display style BC caret 2 equals AB times BH text and AC caret 2 equals AB times R. Summing these two equalities results in B C 2 plus A C 2 equals A B times B H plus A B times A H equals A B times A H plus B H equals A B 2 display style BC caret 2 plus AC caret 2 equals AB times BH plus AB times R equals AB times R plus BH equals AB caret 2, which, after simplification, expresses the Pythagorean theorem B C 2 plus A C 2 equals A B 2 display style BC caret 2 plus AC caret 2 equals AB caret 2. The role of this proof in history is the subject of much speculation. The underlying question is why Euclid did not use this proof, but invented another. One conjecture is that the proof by similar triangles involved a theory of proportions, a topic not discussed until later in the Elements, and that the theory of proportions needed further development at that time. Euclid's proof. In outline, here is how the proof in Euclid's Elements proceeds. The large square is divided into a left and right rectangle. A triangle is constructed that has half the area of the left rectangle. Then another triangle is constructed that has half the area of the square on the leftmost side. These two triangles are shown to be congruent, proving this square has the same area as the left rectangle. This argument is followed by a similar version for the right rectangle and the remaining square. Putting the two rectangles together to reform the square on the hypotenuse, its area is the same as the sum of the area of the other two squares. The details follow. Let A, B, C be the vertices of a right triangle, with a right angle at A. Drop a perpendicular from A to the side opposite the hypotenuse in the square on the hypotenuse. That line divides the square on the hypotenuse into two rectangles, each having the same area as one of the two squares on the legs. For the formal proof, we require four elementary lemmata. If two triangles have two sides of the one equal to two sides of the other, each to each, and the angles included by those sides equal, then the triangles are congruent side angle side. The area of a triangle is half the area of any parallelogram on the same base and having the same altitude. The area of a rectangle is equal to the product of two adjacent sides. The area of a square is equal to the product of two of its sides, follows from 3. Next, each top square is related to a triangle congruent with another triangle related in turn to one of two rectangles making up the lower square. The proof is as follows. Let ACB be a right-angled triangle with right angle cab. On each of the sides BC, AB, and CA, squares are drawn, CBDE, BAGF, and ACIH, in that order. The construction of squares requires the immediately preceding theorems in Euclid, and depends upon the parallel postulate. From A, draw a line parallel to BD and CE. It will perpendicularly intersect BC and DE at K and L, respectively. Join CF and AD, to form the triangles BCF and BDA. Angles CAB and BAG are both right angles, therefore C, A, and G are collinear. Similarly for B, A, and H. Angles CBD and FBA are both right angles, therefore angle AB equals angle FBC, since both are the sum of a right angle and angle ABC. Since AB is equal to FB and BD is equal to BC, triangle AB must be congruent to triangle FBC. Since AKL is a straight line, parallel to BD, then rectangle BDLK has twice the area of triangle AB because they share the base BD and have the same altitude BK, i.e., a line normal to their common base, connecting the parallel lines BD and AL, lemma 2. Since C is collinear with A and G, square BAGF must be twice in area to triangle FBC. Therefore, rectangle BDLK must have the same area as square BAGF equals AB2. Similarly, it can be shown that rectangle CKLE must have the same area as square ACIH equals AC2. Adding these two results, AB2 plus AC2 equals BD times BK plus KL times KC. Since BD KL, BD times BK plus KL times KC. BD BK plus KC equals BD times BC. Therefore, AB2 plus AC2 equals BC2. Since CBDE is a square, this proof, which appears in Euclid's Elements as that of proposition 47 in Book 1, demonstrates that the area of the square on the hypotenuse is the sum of the areas of the other two squares. This is quite distinct from the proof by similarity of triangles, which is conjectured to be the proof that Pythagoras used. Proofs by dissection and rearrangement. We have already discussed the Pythagorean proof, which was a proof by rearrangement. The same idea is conveyed by the leftmost animation below, which consists of a large square, side A plus B, containing four identical right triangles. The triangles are shown in two arrangements, the first of which leaves two squares A2 and B2 uncovered, the second of which leaves square C2 uncovered. The area encompassed by the outer square never changes, and the area of the four triangles is the same at the beginning and the end, so the black square areas must be equal, therefore A2 plus B2. C2. A second proof by rearrangement is given by the middle animation. A large square is formed with area C2, from four identical right triangles with sides A, B and C, fitted around a small central square. Then two rectangles are formed with sides A and B by moving the triangles. Combining the smaller square with these rectangles produces two squares of areas A2 and B2, which must have the same area as the initial large square. The third, rightmost image also gives a proof. The upper two squares are divided as shown by the blue and green shading, into pieces that when rearranged can be made to fit in the lower square on the hypotenuse, or conversely the large square can be divided as shown into pieces that fill the other two. This way of cutting one figure into pieces and rearranging them to get another figure is called dissection. This shows the area of the large square equals that of the two smaller ones. Einstein's proof by dissection without rearrangement. Albert Einstein gave a proof by dissection in which the pieces need not get moved. Instead of using a square on the hypotenuse and two squares on the legs, one can use any other shape that includes the hypotenuse, and two similar shapes that each include one of two legs instead of the hypotenuse. See #similar figures on the three sides. In Einstein's proof, the shape that includes the hypotenuse is the right triangle itself. The dissection consists of dropping a perpendicular from the vertex of the right angle of the triangle to the hypotenuse, thus splitting the whole triangle into two parts. Those two parts have the same shape as the original right triangle, and have the legs of the original triangle as their hypotenuses, and the sum of their areas is that of the original triangle. Because the ratio of the area of a right triangle to the square of its hypotenuse is the same for similar triangles, the relationship between the areas of the three triangles holds for the squares of the sides of the large triangle as well. Algebraic proofs. The theorem can be proved algebraically using four copies of a right triangle with sides A, B and C, arranged inside a square with side C as in the top half of the diagram. The triangles are similar with area 1 2 a b display style tfrac 1 2 ab, while the small square has side b minus a and area b minus a 2. The area of the large square is therefore b minus a 2 plus 4 a b 2 equals b minus a 2 plus 2 a b equals b 2 minus 2 a b plus a 2 plus 2 a b equals a 2 plus b 2. Display style ba caret 2 plus 4 frac ab 2 equals ba caret 2 plus 2 ab equals b caret 2 minus 2 ab plus a caret 2 plus 2 ab equals a caret 2 plus b caret 2. But this is a square with side c and area c2, so c2 equals a 2 plus b 2. Display style c caret 2 equals a caret 2 plus b caret 2. A similar proof uses 4 copies of the same triangle arranged symmetrically around a square with side c, as shown in the lower part of the diagram. This results in a larger square, with side a plus b and area a plus b 2. The 4 triangles and the square side C must have the same area as the larger square b plus a 2 equals c 2 plus 4 a b 2 equals c 2 plus 2 a b. Display style b plus a caret 2 equals c caret 2 plus 4 frac ab 2 equals c caret 2 plus 2 ab, giving c 2 equals b plus a 2 minus 2 a b equals b 2 plus 2 a b plus a 2 minus 2 a b equals a 2 plus b 2. Display style c caret 2 equals b plus a caret 2 minus 2 ab equals b caret 2 plus 2 ab plus a caret 2 minus 2 ab equals a caret 2 plus b caret 2. A related proof was published by future U.S. President James A. Garfield, then a U.S. representative. Instead of a square, it uses a trapezoid, which can be constructed from the square in the second of the above proofs by bisecting along a diagonal of the inner square, to give the trapezoid as shown in the diagram. The area of the trapezoid can be calculated to be half the area of the square, that is 1 2 b plus a 2 Display style frac 1 2 b plus a caret 2. The inner square is similarly halved, and there are only two triangles, so the proof proceeds as above except for a factor of 1 2. Display style frac 1 2, which is removed by multiplying by 2 to give the result. Topic: Proof using differentials. One can arrive at the Pythagorean theorem by studying how changes in a side produce a change in the hypotenuse and employing calculus. The triangle ABC is a right triangle, as shown in the upper part of the diagram, with BC the hypotenuse. At the same time, the triangle lengths are measured as shown, with the hypotenuse of length y, the side AC of length x and the side AB of length a, as seen in the lower diagram part. If x is increased by a small amount dx by extending the side AC slightly to d, then y also increases by dy. These form two sides of a triangle, CDE, which with E chosen so CE is perpendicular to the hypotenuse is a right triangle approximately similar to ABC. Therefore, the ratios of their sides must be the same, that is d y d x equals x y. Display style frac dy dx equals frac x y. This can be rewritten as y d y equals x d x. Display style y dy equals x dx, which is a differential equation that can be solved by direct integration. Y d y equals x d x. Display style int y dy equals int x dx, giving y 2 equals x 2 plus c. Display style y caret 2 equals x caret 2 plus c. The constant can be deduced from x. Topic 0 y. To give the equation y 2 equals x 2 plus a 2. Display style y caret 2 equals x caret 2 plus a caret 2. This is more of an intuitive proof than a formal one. It can be made more rigorous if proper limits are used in place of dx and dy. Topic: Converse. The converse of the theorem is also true. For any three positive numbers a, b, and c such that a2 plus b2 equals c2, there exists a triangle with sides a, b and c, and every such triangle has a right angle between the sides of lengths a and b. An alternative statement is: for any triangle with sides a, b, c, if a2 plus b2 equals c2, then the angle between a and b measures 90 degrees. This converse also appears in Euclid's Elements Book 1, Proposition 48. If in a triangle the square on one of the sides equals the sum of the squares on the remaining two sides of the triangle, then the angle contained by the remaining two sides of the triangle is right. It can be proven using the law of cosines or as follows. Let ABC be a triangle with side lengths a, b, and c, with a2 plus b2. Topic C2. Construct a second triangle with sides of length a and b containing a right angle. By the Pythagorean theorem, it follows that the hypotenuse of this triangle has length c square root a2 plus b2, the same as the hypotenuse of the first triangle. Since both triangles' sides are the same lengths a, b and c, the triangles are congruent and must have the same angles. Therefore, the angle between the side of lengths a and b in the original triangle is a right angle. The above proof of the converse makes use of the Pythagorean theorem itself. The converse can also be proven without assuming the Pythagorean theorem. A corollary of the Pythagorean theorem's converse is a simple means of determining whether a triangle is right, obtuse, or acute, as follows. Let C be chosen to be the longest of the three sides and A plus B greater than C, otherwise there is no triangle according to the triangle inequality. The following statements apply: if A2 plus B2 equals C2, then the triangle is right. If A2 plus B2 greater than C2, then the triangle is acute. If A2 plus B2. Dijkstra has stated this proposition about acute, right, and obtuse triangles in this language: SGN alpha plus beta minus gamma equals SGN A2 plus B2 minus C2, where alpha is the angle opposite to side A, beta is the angle opposite to side B, gamma is the angle opposite to side C, and SGN is the sine function. Topic: Consequences and uses of the theorem. Equals. Topic: Pythagorean triples. Equals. A Pythagorean triple has three positive integers a, b, and c, such that a2 plus b2 equals c2. In other words, a Pythagorean triple represents the lengths of the sides of a right triangle where all three sides have integer lengths. Such a triple is commonly written a, b, c. Some well-known examples are 3, 4, 5, and 5, 12, 13. A primitive Pythagorean triple is one in which a, b and c are coprime. The greatest common divisor of a, b and c is 1. The following is a list of primitive Pythagorean triples with values less than 100. 3, 4, 5, 5, 12, 13, 7, 24, 25, 8, 15, 17, 9, 40, 41, 11, 60, 61, 12, 35, 37, 13, 84, 85, 16, 63, 65, 20, 21, 29, 28, 45, 53, 33, 56, 65, 36, 77, 85, 39, 80, 89, 48, 55, 73, 65, 72, 97. Topic: Incommensurable lengths. One of the consequences of the Pythagorean theorem is that line segments whose lengths are incommensurable, so the ratio of which is not a rational number, can be constructed using a straightedge and compass. Pythagoras's theorem enables construction of incommensurable lengths because the hypotenuse of a triangle is related to the sides by the square root operation. The figure on the right shows how to construct line segments whose lengths are in the ratio of the square root of any positive integer. Each triangle has a side labeled 1, that is the chosen unit for measurement. In each right triangle, Pythagoras's theorem establishes the length of the hypotenuse in terms of this unit. If a hypotenuse is related to the unit by the square root of a positive integer that is not a perfect square, it is a realization of a length incommensurable with the unit, such as square root 2, square root 3, square root 5. For more detail, see quadratic irrational. Incommensurable lengths conflicted with the Pythagorean school's concept of numbers as only whole numbers. The Pythagorean school dealt with proportions by comparison of integer multiples of a common subunit. According to one legend, Hippasus of Metapontum ca. 470 BC was drowned at sea for making known the existence of the irrational or incommensurable. Topic: Complex numbers. For any complex number z equals x plus I y, display style z equals x plus I y, the absolute value or modulus is given by r equals z equals x 2 plus y 2. Display style r equals z equals sqrt x caret 2 plus y caret 2. So the three quantities r, x, and y are related by the Pythagorean equation r 2 equals x 2 plus y 2. Display style r caret 2 equals x caret 2 plus y caret 2. Note that r is defined to be a positive number or zero, but x and y can be negative as well as positive. Geometrically, r is the distance of the z from 0 or the origin O in the complex plane. This can be generalized to find the distance between 2 points, z1 and z2. Say the required distance is given by z1 minus z2 equals x1 minus x2 plus y1 minus y2 display style z underscore 1 z underscore 2 equals sqrt x underscore 1 x underscore 2 caret 2 plus y underscore 1 y underscore 2 caret 2. So again, they are related by a version of the Pythagorean equation z 1 minus z 2 equals x 1 minus x 2 plus y 1 minus y 2 display style z underscore 1 z underscore 2 caret 2 equals x underscore 1 x underscore 2 caret 2 plus y underscore 1 y underscore 2 caret 2. Topic: Euclidean distance in various coordinate systems. The distance formula in Cartesian coordinates is derived from the Pythagorean theorem. If x1, y1, and x2, y2 are points in the plane, then the distance between them, also called the Euclidean distance, is given by x1 minus x2 plus y1 minus y2 display style sqrt x underscore 1 x underscore 2 caret 2 plus y underscore 1 y underscore 2 caret 2. More generally, in Euclidean n-space, the Euclidean distance between 2 points equals 1 2 a n Display style a equals a underscore 1 a underscore 2 dots a underscore n and b equals b 1 b 2 b n. Display style b equals b underscore 1 b underscore 2 dots b underscore n is defined by generalization of the Pythagorean theorem as a 1 minus b 1 2 plus a 2 minus b 2 plus a n minus b n 2 equals I equals 1 n a I minus b I 2. Display style sqrt a underscore 1 b underscore 1 caret 2 plus a underscore 2 b underscore 2 caret 2 plus cdots plus a underscore n b underscore n caret 2 equals sqrt sum underscore I equals 1 caret n a underscore I b underscore I caret 2. If Cartesian coordinates are not used, for example, if polar coordinates are used in 2 dimensions or, in more general terms, if curvilinear coordinates are used, the formulas expressing the Euclidean distance are more complicated than the Pythagorean theorem, but can be derived from it. A typical example where the straight line distance between 2 points is converted to curvilinear coordinates can be found in the applications of Legendre polynomials in physics. The formulas can be discovered by using Pythagoras's theorem with the equations relating the curvilinear coordinates to Cartesian coordinates. For example, the polar coordinates r, theta can be introduced as x equals r cos theta, y equals r sin theta. Display style x equals r cos theta, y equals r sin theta. Then 2 points with locations r1, theta 1, and r2, theta 2 are separated by a distance s. S 2 equals x 1 minus x 2 plus y 1 minus y 2 equals r 1 cos theta 1 minus r 2 cos theta 2 plus r 1 sin theta 1 minus r 2 sin theta 2 display style s caret 2 equals x underscore 1 x underscore 2 caret 2 plus y underscore 1 y underscore 2 caret 2 equals r underscore 1 cos theta underscore 1 r underscore 2 cos theta underscore 2 caret 2 plus r underscore 1 sin theta underscore 1 r underscore 2 sin theta underscore 2 caret 2. Performing the squares and combining terms, the Pythagorean formula for distance in Cartesian coordinates produces the separation in polar coordinates as S 2 equals R 1 2 plus R 2 2 minus 2 R 1 R 2 cos theta 1 cos theta 2 plus sin theta 1 sin theta 2 equals R 1 2 plus R2 2 minus 2 R1 R2 cos theta 1 minus theta 2 equals R1 2 plus R2 2 minus 2 R1 R2 cos delta theta. Display style begin aligned S caret 2 and equals R underscore 1 caret 2 plus R underscore 2 caret 2 2 R underscore 1 R underscore 2 left cos theta underscore 1 cos theta underscore 2 plus sin theta underscore 1 sin theta underscore 2 right and equals R underscore 1 caret 2 plus R underscore 2 caret 2 2 R underscore 1 R underscore 2 cos left theta underscore 1 theta underscore 2 right and equals R underscore 1 caret 2 plus R underscore 2 caret 2 2 R underscore 1 R underscore 2 cos delta theta end aligned using the trigonometric product to some formulas. This formula is the law of cosines, sometimes called the generalized Pythagorean theorem. From this result, for the case where the radii to the two locations are at right angles, the enclosed angle doth equals pi 2, and the form corresponding to Pythagoras's theorem is regained. S 2 equals R 1 2 plus R 2 2 display style S caret 2 equals R underscore 1 caret 2 plus R underscore 2 caret 2. The Pythagorean theorem, valid for right triangles, therefore is a special case of the more general law of cosines, valid for arbitrary triangles. Pythagorean trigonometric identity. In a right triangle with sides A, B and hypotenuse C, trigonometry determines the sine and cosine of the angle θ between side A and the hypotenuse as sin θ equals B C cos θ equals A C. Display style sin theta equals frac B C quad cos theta equals frac A C. From that it follows cos 2 theta plus sin 2 theta equals A 2 plus B 2 C 2 equals 1. Display style cos caret 2 theta plus sin caret 2 theta equals frac A caret 2 plus B caret 2 C caret 2 equals 1, where the last step applies Pythagoras's theorem. This relation between sine and cosine is sometimes called the fundamental Pythagorean trigonometric identity. In similar triangles, the ratios of the sides are the same regardless of the size of the triangles, and depend upon the angles. Consequently, in the figure, the triangle with hypotenuse of unit size has opposite side of size sin θ and adjacent side of size cos θ in units of the hypotenuse. Topic: relation to the cross product. The Pythagorean theorem relates the cross product and dot product in a similar way. A times b2 plus a b2 equals a 2b2. Display style math BF a times math BF b caret 2 plus math BF a CDOT math BF b caret 2 equals math BF a caret 2 math BF b caret 2. This can be seen from the definitions of the cross product and dot product as a times b equals a b n sin theta, a b equals a b cos theta. Display style begin aligned math BF a times math BF b and equals ab math BF n sin theta math BF a CDOT math BF b and equals ab cos theta end aligned with n, a unit vector normal to both a and b. The relationship follows from these definitions and the Pythagorean trigonometric identity. This can also be used to define the cross product. By rearranging, the following equation is obtained: a times b 2 equals a 2 b 2 minus a b 2. Display style math BF a times math BF b caret 2 equals math BF a caret 2 math BF b caret 2 math BF a CDOT math BF b caret 2. This can be considered as a condition on the cross product and so part of its definition, for example in 7 dimensions. Topic: Generalizations. Topic: Similar figures on the three sides. A generalization of the Pythagorean theorem extending beyond the areas of squares on the three sides to similar figures was known by Hippocrates of Chios in the 5th century BC, and was included by Euclid in his Elements. If one erects similar figures, see Euclidean geometry, with corresponding sides on the sides of a right triangle, then the sum of the areas of the ones on the two smaller sides equals the area of the one on the larger side. This extension assumes that the sides of the original triangle are the corresponding sides of the three congruent figures, so the common ratios of sides between the similar figures are a, b, c. While Euclid's proof only applied to convex polygons, the theorem also applies to concave polygons and even to similar figures that have curved boundaries but still with part of a figure's boundary being the side of the original triangle. The basic idea behind this generalization is that the area of a plane figure is proportional to the square of any linear dimension, and in particular is proportional to the square of the length of any side. Thus, if similar figures with areas a, b and c are erected on sides with corresponding lengths a, b and c, then a 2 equals b 2 equals c 2. Display style frac a caret 2 equals frac b caret 2 equals frac c caret 2. A plus b equals a 2 c 2 c plus b 2 c 2 c. Display style right arrow a plus b equals frac a caret 2 c caret 2 c plus frac b caret 2 c caret 2 c. But by the Pythagorean theorem, a2 plus b2. Topic c2, so a plus b. C. Conversely, if we can prove that a plus b equals C for three similar figures without using the Pythagorean theorem, then we can work backwards to construct a proof of the theorem. For example, the starting center triangle can be replicated and used as a triangle C on its hypotenuse, and two similar right triangles A and B constructed on the other two sides, formed by dividing the central triangle by its altitude. The sum of the areas of the two smaller triangles therefore is that of the third, thus A plus B equals C, and reversing the above logic leads to the Pythagorean theorem A2 plus B2 equals C2. See also Einstein's proof by dissection without rearrangement. Topic: Law of cosines. The Pythagorean theorem is a special case of the more general theorem relating the lengths of sides in any triangle, the law of cosines. A 2 plus b 2 minus 2 a b cos theta equals c 2. Display style a caret 2 plus b caret 2 minus 2 ab cos theta equals c caret 2, where theta is the angle between sides A and B. When theta is 90 degrees pi 2 radians, then cos theta equals 0, and the formula reduces to the usual Pythagorean theorem. Topic: Arbitrary triangle. At any selected angle of a general triangle of sides A, B, C, inscribe an isosceles triangle such that the equal angles at its base θ are the same as the selected angle. Suppose the selected angle θ is opposite the side labeled C. Inscribing the isosceles triangle forms triangle AB with angle θ opposite side A and with side R along C. A second triangle is formed with angle θ opposite side B and a side with length S along C, as shown in the figure. Thabit ibn Qurra stated that the sides of the three triangles were related as A 2 plus B 2 equals C R plus S. Display style a caret 2 plus b caret 2 equals c r plus s. As the angle θ approaches pi 2, the base of the isosceles triangle narrows, and lengths r and s overlap less and less. When θ topic pi 2 ADB becomes a right triangle r plus s. C, and the original Pythagorean theorem is regained. One proof observes that triangle ABC has the same angles as triangle ABD, but in opposite order. The two triangles share the angle at vertex B, both contain the angle θ, and so also have the same third angle by the triangle postulate. Consequently, ABC is similar to the reflection of ABD, the triangle DBA in the lower panel. Taking the ratio of sides opposite and adjacent to θ, C A equals A R. Display style frac C A equals frac A R. Likewise, for the reflection of the other triangle, C B equals B S. Display style frac C B equals frac B S. Clearing fractions and adding these two relations, C R plus C S equals A 2 plus B 2 Display style CR plus CS equals a caret 2 plus B caret 2. The required result. The theorem remains valid if the angle theta display style theta is obtuse, so the lengths R and S are non-overlapping. Topic: General triangles using parallelograms. Pappus's area theorem is a further generalization, that applies to triangles that are not right triangles, using parallelograms on the three sides in place of squares. Squares are a special case, of course. The upper figure shows that for a scalene triangle, the area of the parallelogram on the longest side is the sum of the areas of the parallelograms on the other two sides, provided the parallelogram on the long side is constructed as indicated. The dimensions labeled with arrows are the same, and determine the sides of the bottom parallelogram. This replacement of squares with parallelograms bears a clear resemblance to the original Pythagoras's theorem, and was considered a generalization by Pappus of Alexandria in 4. The lower figure shows the elements of the proof. Focus on the left side of the figure. The left green parallelogram has the same area as the left blue portion of the bottom parallelogram because both have the same base B and height h. However, the left green parallelogram also has the same area as the left green parallelogram of the upper figure, because they have the same base, the upper left side of the triangle, and the same height normal to that side of the triangle. Repeating the argument for the right side of the figure, the bottom parallelogram has the same area as the sum of the two green parallelograms. Topic: Solid geometry. In terms of solid geometry, Pythagoras's theorem can be applied to three dimensions as follows. Consider a rectangular solid as shown in the figure. The length of diagonal BD is found from Pythagoras's theorem as B D 2 equals B C 2 plus C D 2. Display style overline BD caret 2 equals overline BC caret 2 plus overline CD caret 2, where these three sides form a right triangle. Using horizontal diagonal BD and the vertical edge AB, the length of diagonal AD then is found by a second application of Pythagoras's theorem as A D 2 equals A B 2 plus B D 2. Display style overline AD caret 2 equals overline AB caret 2 plus overline BD caret 2, or doing it all in one step. A D 2 equals A B 2 plus B C 2 plus C D 2. Display style overline AD caret 2 equals overline AB caret 2 plus overline BC caret 2 plus overline CD caret 2. This result is the three-dimensional expression for the magnitude of a vector v, the diagonal AD, in terms of its orthogonal components vk, the three mutually perpendicular sides v 2 equals k equals 1 3 v k 2. Display style Math v caret 2 equals sum underscore k equals 1 caret 3 Math v underscore k caret 2. This one-step formulation may be viewed as a generalization of Pythagoras's theorem to higher dimensions. However, this result is really just the repeated application of the original Pythagoras's theorem to a succession of right triangles in a sequence of orthogonal planes. A substantial generalization of the Pythagorean theorem to three dimensions is de Goua's theorem, named for Jean-Paul de Gouas de Malves. If a tetrahedron has a right-angle corner like a corner of a cube, then the square of the area of the face opposite the right-angle corner is the sum of the squares of the areas of the other three faces. This result can be generalized as in the n-dimensional Pythagorean theorem. Let x 1 x 2 x n display style x underscore 1 x underscore 2 l dots x underscore n be orthogonal vectors in n. Consider the n-dimensional simplex S with vertices 0 x 1 x n display style 0 x underscore 1 l dots x underscore n. Think of the n-1 dimensional simplex with vertices x 1 x n display style x underscore 1 l dots x underscore n, not including the origin as the hypotenuse of S and the remaining n-1 dimensional faces of S as its legs. Then the square of the volume of the hypotenuse of S is the sum of the squares of the volumes of the n legs. This statement is illustrated in three dimensions by the tetrahedron in the figure. The hypotenuse is the base of the tetrahedron at the back of the figure, and the legs are the three sides emanating from the vertex in the foreground. As the depth of the base from the vertex increases, the area of the legs increases, while that of the base is fixed. The theorem suggests that when this depth is at the value creating a right vertex, the generalization of Pythagoras's theorem applies. In a different wording, given an n-rectangular n-dimensional simplex, the square of the n-1 content of the facet opposing the right vertex will equal the sum of the squares of the n-1 contents of the remaining facets. Topic: Inner product spaces. The Pythagorean theorem can be generalized to inner product spaces, which are generalizations of the familiar two-dimensional and three-dimensional Euclidean spaces. For example, a function may be considered as a vector with infinitely many components in an inner product space, as in functional analysis. In an inner product space, the concept of perpendicularity is replaced by the concept of orthogonality. Two vectors v and w are orthogonal if their inner product v w display style Langle math BF v math BF w rangle is 0. The inner product is a generalization of the dot product of vectors. The dot product is called the standard inner product or the Euclidean inner product. However, other inner products are possible. The concept of length is replaced by the concept of the norm v of a vector v, defined as v display style L vert math BF v r vert equivalent sqrt Langle math BF v math BF v rangle. In an inner product space, the Pythagorean theorem states that for any two orthogonal vectors v and w we have v plus w 2 equals v 2 plus w 2 display style left math BF v plus math BF w right caret 2 equals left math BF v right caret 2 plus left math BF w right caret 2. Here the vectors v and w are akin to the sides of a right triangle with hypotenuse given by the vector sum v plus w. This form of the Pythagorean theorem is a consequence of the properties of the inner product v plus w 2 equals v plus w v plus w equals v v plus w w plus v w plus w v equals v 2 plus w 2. Display style left math BF v plus math BF w right caret 2 equals Langle math BF v plus w math BF v plus w wrangle equals Langle math BF v wrangle plus Langle math BF w math BF w wrangle plus Langle math BF v w wrangle plus Langle math BF w v wrangle equals left math BF v right caret 2 plus left math BF w right caret 2, where the inner products of the cross terms are zero because of orthogonality. A further generalization of the Pythagorean theorem in an inner product space to non-orthogonal vectors is the parallelogram law. 2 v 2 plus 2 w 2 equals v plus w 2 plus v minus w 2. Display style 2 math BF v caret 2 plus 2 math BF w caret 2 equals math BF v plus w caret 2 plus math BF vw caret 2, which says that twice the sum of the squares of the lengths of the sides of a parallelogram is the sum of the squares of the lengths of the diagonals. Any norm that satisfies this equality is ipso facto a norm corresponding to an inner product. The Pythagorean identity can be extended to sums of more than two orthogonal vectors. If v1, v2, vn are pairwise orthogonal vectors in an inner product space, then application of the Pythagorean theorem to successive pairs of these vectors as described for 3 dimensions in the section on solid geometry results in the equation k equals 1 n v k 2 equals k equals 1 n v k 2. Display style left sum underscore k equals 1 caret n math BF v underscore k right caret 2 equals sum underscore k equals 1 caret n math BF v underscore k caret 2. Topic: Sets of m-dimensional objects in n-dimensional space. Another generalization of the Pythagorean theorem applies to Lebesgue measurable sets of objects in any number of dimensions. Specifically, the square of the measure of an m-dimensional set of objects in one or more parallel m-dimensional flats in n-dimensional Euclidean space is equal to the sum of the squares of the measures of the orthogonal projections of the objects onto all m-dimensional coordinate subspaces. In mathematical terms, mu m s 2 equals I equals 1 x mu 2 M P I display style mu underscore ms caret 2 equals sum underscore I equals 1 caret x math BF mu caret 2 underscore MP underscore I, where mu M display style mu underscore M is a measure in m dimensions, a length in one dimension, an area in two dimensions, a volume in three dimensions, etc. S display style S is a set of one or more non-overlapping m-dimensional objects in one or more parallel m-dimensional flats in n-dimensional Euclidean space. Mu M S display style mu underscore ms is the total measure sum of the set of m-dimensional objects P display style P represents an m-dimensional projection of the original set onto an orthogonal coordinate subspace. Mu M P I display style mu underscore MP underscore I is the measure of the m-dimensional set projection onto m-dimensional coordinate subspace I display style I. Because object projections can overlap on a coordinate subspace, the measure of each object projection in the set must be calculated individually, then measures of all projections added together to provide the total measure for the set of projections on the given coordinate subspace. X display style X is the number of orthogonal, m-dimensional coordinate subspaces in n-dimensional space Rn onto which the m-dimensional objects are projected Mn. X equals n m equals n m n minus m. Display style x equals binom n m equals frac n m n m. Topic: Non-Euclidean geometry. The Pythagorean theorem is derived from the axioms of Euclidean geometry, and in fact, the Pythagorean theorem given above does not hold in a non-Euclidean geometry. The Pythagorean theorem has been shown, in fact, to be equivalent to Euclid's parallel fifth postulate. In other words, in non-Euclidean geometry, the relation between the sides of a triangle must necessarily take a non-Pythagorean form. For example, in spherical geometry, all three sides of the right triangle, say A, B, and C, bounding an octant of the unit sphere have length equal to pi 2, and all its angles are right angles, which violates the Pythagorean theorem because A2 plus B2 does not equal C2. Here two cases of non-Euclidean geometry are considered: spherical geometry and hyperbolic plane geometry. In each case, as in the Euclidean case for non-right triangles, the result replacing the Pythagorean theorem follows from the appropriate law of cosines. However, the Pythagorean theorem remains true in hyperbolic geometry and elliptic geometry if the condition that the triangle be right is replaced with the condition that two of the angles sum to the third, say A plus B equals C. The sides are then related as follows: the sum of the areas of the circles with diameters A and B equals the area of the circle with diameter C. Topic: Spherical geometry. For any right triangle on a sphere of radius r, for example, if gamma in the figure is a right angle, with sides a, b, c, the relation between the sides takes the form cos c r equals cos a r cos b r. Display style cos left frac c r right equals cos left frac a r right cos left frac b r right. This equation can be derived as a special case of the spherical law of cosines that applies to all spherical triangles. Cos c r equals cos a r cos b r plus sin a r sin b r cos gamma. Display style cos left frac c r right equals cos left frac a r right cos left frac b r right plus sin left frac a r right sin left frac b r right cos gamma. By expressing the Maclaurin series for the cosine function as an asymptotic expansion with the remainder term in big O notation, cos x equals 1 minus x 2 plus O x 4 as x 0. Display style cos x equals 1 frac x caret 2 plus O x caret 4 text as x to 0. It can be shown that as the radius r approaches infinity and the arguments a, r, b, r, and c, r tend to 0, the spherical relation between the sides of a right triangle approaches the Euclidean form of the Pythagorean theorem. Substituting the asymptotic expansion for each of the cosines into the spherical relation for a right triangle yields 1 minus 1 2 c r 2 plus O 1 r 4 equals 1 minus 1 2 a r 2 plus O 1 r 4 1 minus 1 2 b r 2 plus O 1 r 4 as r infinity. Display style 1 frac 1 2 left frac c r right caret 2 plus O left frac 1 r caret 4 right equals left 1 frac 1 2 left frac a r right caret 2 plus O left frac 1 r caret 4 right left 1 frac 1 2 left frac b r right caret 2 plus O left frac 1 r caret 4 right text as r to inf t. The constants A4, B4, and C4 have been absorbed into the big O remainder terms since they are independent of the radius r. This asymptotic relationship can be further simplified by multiplying out the bracketed quantities, cancelling the ones, multiplying through by -2, and collecting all the error terms together. C r 2 equals a r 2 plus b r 2 plus O 1 r 4 as r infinity. Display style left frac c r right caret 2 equals left frac a r right caret 2 plus left frac b r right caret 2 plus o left frac 1 r caret 4 right text as r to inf t. After multiplying through by R2, the Euclidean Pythagorean relationship C2 equals A2 plus B2 is recovered in the limit as the radius r approaches infinity, since the remainder term tends to 0. C2 equals A2 plus B2 plus O 1 R 2 as R infinity. Display style c caret 2 equals a caret 2 plus b caret 2 plus o left frac 1 r caret 2 right text as r to inf t. For small right triangles a b sin 2 c 2 r equals sin 2 a 2 r plus sin 2 b 2 r minus 2 sin 2 a 2 r sin 2 b 2 r. Display style sin caret 2 frac c 2 r equals sin caret 2 frac a 2 r plus sin caret 2 frac b 2 r minus 2 sin caret 2 frac a 2 r sin caret 2 frac b 2 r. Topic: Hyperbolic geometry. In a hyperbolic space with uniform curvature -1, R2, for a right triangle with legs a, b, and hypotenuse c, the relation between the sides takes the form cosh c r equals cosh a r cosh b r. Display style cosh frac c r equals cosh frac a r cosh frac b r, where cosh is the hyperbolic cosine. This formula is a special form of the hyperbolic law of cosines that applies to all hyperbolic triangles. Cosh c r equals cosh a r cosh b r minus sine a r sine b r cos gamma. Display style cosh frac c r equals cosh frac a r cosh frac b r sine frac a r sine frac b r cos gamma, with gamma the angle at the vertex opposite the side c. By using the Maclaurin series for the hyperbolic cosine, cosh x approximately equals 1 plus by 2 halves, it can be shown that as a hyperbolic triangle becomes very small, that is, as a, b, and c all approach 0, the hyperbolic relation for a right triangle approaches the form of Pythagoras's theorem. For small right triangles a, b sine 2 c 2 r equals sine 2 a 2 r plus sine 2 b 2 r plus 2 sine 2 a 2 r sine 2 b 2 r. Display style sine caret 2 frac c 2 r equals sine caret 2 frac a 2 r plus sine caret 2 frac b 2 r plus 2 sine caret 2 frac a 2 r sine caret 2 frac b 2 r. Topic: very small triangles. For any uniform curvature k positive, 0, or negative, in very small right triangles, k, a2, k, b2 c2 equals a2 plus b2 minus k3 a2 b2 minus k2 45 a2 b2 a2 plus b2 minus 2 k 3945 a2 b2 a2 minus b2 2 plus o k 4 c 10 Display style c caret 2 equals a caret 2 plus b caret 2 frac k 3 a caret 2 b caret 2 frac k caret 2 45 a caret 2 b caret 2 a caret 2 plus b caret 2 frac 2 k caret 3 945 a caret 2 b caret 2 a caret 2 b caret 2 plus o k caret 4 c caret 10. Topic: Differential geometry. On an infinitesimal level, in three-dimensional space, Pythagoras's theorem describes the distance between two infinitesimally separated points as d s 2 equals d x 2 plus d y 2 plus d z 2. Display style ds caret 2 equals dx caret 2 plus dy caret 2 plus dz caret 2. With disabilities the element of distance and dx, dy, dz the components of the vector separating the 2 points. Such a space is called a Euclidean space. However, in Riemannian geometry, a generalization of this expression useful for general coordinates not just Cartesian and general spaces not just Euclidean takes the form d s 2 equals I j n g I j d x I d x j. Display style ds caret 2 equals sum underscore I j caret n g underscore I j dx underscore I dx underscore j, which is called the metric tensor. Sometimes, by abuse of language, the same term is applied to the set of coefficients Gij. It may be a function of position, and often describes curved space. A simple example is Euclidean flat space expressed in curvilinear coordinates. For example, in polar coordinates d s 2 equals d r 2 plus r 2 d theta 2. Display style ds caret 2 equals doctor caret 2 plus r caret 2 d theta caret 2. Topic: History. There is debate whether the Pythagorean theorem was discovered once, or many times in many places, and the date of first discovery is uncertain, as is the date of the first proof. According to Joran Freiberg, a historian of mathematics, evidence indicates that the Pythagorean theorem was well known to the mathematicians of the First Babylonian dynasty 20th to 16th centuries BC, which would have been over 1,000 years before Pythagoras was born, thus an example of Stigler's law of eponymy. Yale's Institute for the Preservation of Cultural Heritage's 3D scan of a cuneiform tablet depicting the proof is one of their mostly widely used images. Other sources, such as a book by Leon Lederman and Dick Teresi, mention that Pythagoras discovered the theorem, although Teresi subsequently stated that the Babylonians developed the theorem at least 1500 years before Pythagoras was born. The history of the theorem can be divided into 4 parts: knowledge of Pythagorean triples, knowledge of the relationship among the sides of a right triangle, knowledge of the relationships among adjacent angles, and proofs of the theorem within some deductive system. Bartel Leendert van der Waerden (1903–1996) conjectured that Pythagorean triples were discovered algebraically by the Babylonians. Written between 2000 and 1786 BC, the Middle Kingdom Egyptian Berlin Papyrus 6619 includes a problem whose solution is the Pythagorean triple 6, 8, 10, but the problem does not mention a triangle. The Mesopotamian tablet Plimpton 322, written between 1790 and 1750 BC during the reign of Hammurabi the Great, contains many entries closely related to Pythagorean triples. In India, the Bodhayana Sulba Sutra, the dates of which are given variously as between the 8th and 5th century BC, contains a list of Pythagorean triples discovered algebraically, a statement of the Pythagorean theorem, and a geometrical proof of the Pythagorean theorem for an isosceles right triangle. The Apastamba Sulba Sutra c. 600 BC contains a numerical proof of the general Pythagorean theorem, using an area computation. Van der Waerden believed that, "...it was certainly based on earlier traditions." Carl Boyer states that the Pythagorean theorem in Sulba Sutram may have been influenced by ancient Mesopotamian math, but there is no conclusive evidence in favor or opposition of this possibility. With contents known much earlier, but in surviving texts dating from roughly the 1st century BC, the Chinese text Zhoubi Suanjing, Zhoubi the arithmetical classic of the gnomon and the circular paths of heaven, gives a reasoning for the Pythagorean theorem for the 3, 4, 5 triangle. In China it is called the Gugu theorem. Gogu Dingli. During the Han dynasty 202 BC to 220 AD, Pythagorean triples appear in the 9 chapters on the mathematical art, together with a mention of right triangles. Some believe the theorem arose first in China, where it is alternatively known as the Shanggao theorem. Shanggao Dingli, named after the Duke of Zhou's astronomer and mathematician, whose reasoning composed most of what was in the Zhoubi Suanjing. Pythagoras, whose dates are commonly given as 569 to 475 BC, used algebraic methods to construct Pythagorean triples, according to Proclus's commentary on Euclid. Proclus, however, wrote between 410 and 485 AD. According to Thomas L. Heath (1861–1940), no specific attribution of the theorem to Pythagoras exists in the surviving Greek literature from the 5 centuries after Pythagoras lived. However, when authors such as Plutarch and Cicero attributed the theorem to Pythagoras, they did so in a way which suggests that the attribution was widely known and undoubted. Whether this formula is rightly attributed to Pythagoras personally, one can safely assume that it belongs to the very oldest period of Pythagorean mathematics. Around 400 BC, according to Proclus, Plato gave a method for finding Pythagorean triples that combined algebra and geometry. Around 300 BC, in Euclid's Elements, the oldest extant axiomatic proof of the theorem is presented. See also Notes